what we've been doing is discussing the Euler equations in this axisymmetric without swirl. And so here we assume that a three-dimensional, a vector field U on R3 has the form. Well, so first of all, the component functions are only functions of R, the distance from the z-axis, and z. And and we assume, in addition, that that there is no theta component. And so this is the axisymmetric without swirl ansatz. And we saw that in this setting, and so the notation I'm using is that the vector U denotes the vector field R3, and the U without an arrow on top will denote the thing in the half plane. It satisfies, well, okay, the same. In fact, really the same equation. The Euler equation looks exactly the same. And the only thing that changes is the divergence-free condition. And the normal component vanishes on the boundary of H here. H is the half plane. Okay, so the natural domain for the coordinates we're interested in. Okay, and so we started looking at basic properties of this equation. And we actually considered a more general equation, which is D is the domain in R2. I need some time also. And here B is a function, positive function, which is given. And one usually assumes smooth, or at least C1. And again, the normal component vanishes on the boundary. Okay. And so this is sometimes called the lake equation because it can describe the flow of water in a lake. Or an incompressible fluid, inviscid incompressible fluid in a shallow basin. The name lake equation doesn't really apply, so it also arises not only from Euler with cylindrical symmetry, but from Euler in higher dimensions with what you might call, say, bi-axis symmetry. In my opinion, the word lake equation is a bit inappropriate for that. Anyway, that's this. So we started talking about properties of this equation, and we saw that. What did we see? Okay, so we define the vorticity as usual, the orthogonal gradient of U, where, well, this is what it always means. So on half space, I would write minus dz comma dr. So this satisfies its material derivative, not of the vorticity, but of the vorticity weighted by this function b is 0. And so what this says is that the quantity that's transported by the flow is not vorticity, it's vorticity over b. So for x, a particle trajectory map, and x times 0 is alpha. For such a function, we have omega divided by the depth function is transported along these particle trajectories. Okay, b is independent of time. We also saw this, and we saw that there's a conserved energy. If, as usual, we have to assume sufficient decay for this. Okay, so then here's a remark, which is, what does this what's this divergence-free condition mean? Well, let me just, and so, for example, for Euler equations with in this axisymmetric without swirl setting, axisymmetric without swirl setting, we have the divergence of r times u is equal to 0. And so it's a fact that for D in Rn, let's who knows what connected, etc. And for a vector field B, sorry, for a non-negative function D, let's make it be C1. We have if U is a vector field, with x d cross 0t to d being the associated particle trajectory map. And I should have put a time in here. Then let's put it this way. The divergence-free condition holds. In the space-time domain, if and only if the flow phi preserves not the, if and only if the flow phi preserves, well, let me write it down, the integral over the image under the flow of and so this is for all, here's this is for all x and t, and this would be for all O subset d and t in 0, capital T, where x of O and t is just the image as we've done before. Okay, and so this is the same as saying that the flow X preserves the measure B of X dx. Okay, so okay, so for example, if we look back up here, this is totally natural because, well, we know that this is a reduction to a new coordinate system of the 3D Euler. We know that the 3D Euler preserves volume, just a Lebesgue measure. And we also know that Lebesgue measure that in this reduction, if I have a subset of the RZ half space, then that corresponds to a, the rotationally, the cylindrically symmetric object generated by that subset. And I know that the volume of that object will be the integral over this section in the RZ half plane of R dr dz times, I guess, pi. And so preserving volume in R3 is the same as preserving R dr dz in R2. And according to this fact I've just stated, this modified divergence free condition exactly says that the measure R dr dz is preserved by the flow, which has to be because it's because it comes from a volume preserving thing in R3. Okay, and so let me see. The proof of this fact is a lot like the proof that I omitted earlier, that a flow is volume preserving if and only. In fact, we can see that by taking B equal to 1, we can see that a special case of this is the assertion that a flow is volume preserving if and only if the associated velocity field is divergence free, where then volume is just ordinary volume in the ordinary sense. And so we stated this earlier and didn't give the proof. Let's sketch the proof now for completeness. So in general, so the key fact is at least under this approach, the key fact is that if I have, so what I'll need to do in verifying this up here is I'll need to do a change of variables in the integral on the right-hand side. And when I do that, I'll need to change variables using this particle trajectory map. And when I do that, I'll get a Jacobian determinant. And so the key fact is that if I need to know how the Jacobian determinant changes along streamlines. And so this is a calculation that you may have seen or you may have done. And so here, again, I'm assuming that X is the particle trajectory map generated by the flow U, by the velocity field U. Okay, and so the key fact is that when we differentiate the determinant, the Jacobian determinant, we get this factor involving the divergence of U. And so this reduces to the fact that when you differentiate the Jacobian determinant at the identity, then you get the when you differentiate, say, referencing the derivative of the determinant function at the identity is the trace. which is pretty easy. And so, so using this, well, we find that if I look at the if I differentiate this, these should be partial integers, sorry. If I then include the weight b, I will have, what is it? And so I'll have a gradient b the gradient with respect to x times the derivative of x with respect to t, which is exactly u. And that will be multiplied by the determinant plus the, let's write this all as plus the gradient of u at xt multiplied by b. And the whole thing is evaluated with x being the point on the trajectory map, and it's all multiplied by the Jacobian determinant. And so I can see that this is just the divergence of b, u, times the Jacobian determinant. Okay, and so the conclusion is that this quantity b times the Jacobian determinant is constant along particle trajectories, if and only if the divergence of b times u vanishes. And so if and only if, and so if this is constant along particle trajectories, well, I can integrate down to time. I can look at its value at time 0. At time 0, we know that the particle trajectory map, capital X, is the identity. And so this determinant becomes 1, and then b just becomes b of alpha. For all alpha and t in the time interval I'm considering. Okay, and so then, so let me see. Okay, so now I can prove the equivalence, and so I wanted to prove that this is equivalent to this volume preserving character. And so let's then look at this integral I have to evaluate. So I'm looking at the integral. I called it x of o t b of x dx. And I'll just do the obvious change of variables. I'll say x is capital X of alpha t, and then so I can write sort of formally dx is this Jacobian determinant times d alpha. And so then making this change of rules, I find that this equals the integral. So this change of rules, of course, transforms the moving domain x of ot to the original domain O. And then I'll have a b of alpha that alpha x of alpha t d. Sorry, this is b of x of alpha t. And but then by the earlier computation, this is and so then the point is that this is equal to for all O and T if and only if. This holds. Okay, and so we can see that. So this proves the claim that this modified divergence precondition preserves this modified volume, which again is totally natural in our context. Okay, so this is sort of filling in something I skipped earlier. Okay, there was one more thing I forgot to. One more conservation law. I don't think I did this last time. Of equation star. And so what I want to do is I'm going to write the vorticity equation in a certain form. I've already written it here. And so here there were some computations I omitted where I have to take the orthogonal gradient, where I take the orthogonal divergence of this u dot grad u, and you have to mess around a little bit to get things in the form I've written here. But another thing I can do is I can simply, if I take the orthogonal divergence of this, that will give me dt of vorticity. And here, let me just not, well, okay, what can I do? We can write this, if I wish, I can rewrite this as I can rewrite it in this form. Okay, and so because if I carry out the differentiation, I'll get a term involving the divergence of bu times u, which vanishes, and I'll get a term involving u dot grad u times b divided by b. Okay, and so I can rewrite the equation in divergence form, and then I can take the orthogonal gradient. The pressure will vanish as always, and then I just have an equation with two derivatives on the nonlinear term. So I can multiply by test function, integrate by parts, and we find the following. So multiply by phi, I don't know what, in C1 of the domain D. And, or let's say, apply, okay, sorry. So we write in divergence form. And then, okay, it's not quite divergence form, it's almost divergence form. Then we multiply by test function. And then we integrate by parts. And we find that and we integrate. And we find that the integral of the test function times the vorticity will be, so I have, I think I have, okay, I have grad perp phi. I guess we have this. Grad perp phi over b, the divergence of that, times b and u tensor u. Okay, and so this is a 2x2 matrix with ij entries, and so this means I multiply the ij entry by ui uj and integrate. And so I want to ask, when do I get a conserved quantity out of this? So when does the right-hand side equal 0? And so the entries of this are, well, there's a d I phi over b and a dj. Okay, and really, I should, you know, these are, I haven't, this isn't the ij entry, it's the, you know, it's the, so for example, the 1, 2 entry would be, anyway, so, but this is what all the entries have this form. There's some anti-symmetric tensors sometimes if we want to write it correctly. And so one way that this can, one way that the right-hand side can equal 0 is if all these quantities vanish. And I can see that's really got to be rare, because it's like 4 equations and phi is a function of 2 variables. I want 4 second derivatives to vanish. That we should not expect this to happen. We should not expect to find non-trivial phi. With this property. But in general, the count of equations and unknowns is just too unfavorable. But if phi is a function, if the weight b is a function of a single variable, say, then what happens? Then we should be able to do this. So then, let's see. This says that okay, so we should not be able to find a non-trivial phi in general such that this quantity vanishes. We saw before when we were looking at conserved quantities for Euler in 2 and 3 dimensions that all the ones I know of that involve multiplying the vorticity by some test function and getting a conserved quantity, in fact, involve things where the corresponding property holds, where you get some combination of derivatives of the where when you compute this set identity, the right-hand side identity vanishes. I guess it would be enough for this combination of derivatives to be anti-symmetric. Even that's 3 equations and 2 unknowns. It seems a bit unfavorable. Anyway, so this is true. So di phi over b is a constant. That depends on right. So I integrate in the xj directions, and so it'll depend on x I. And in other words, di phi is b of x. I don't know what 1 tilde times c of xi for I being 1 and 2. And I think I can do this if, so it should be okay. So this will be true as if so I just take phi to be I just take the antiderivative of b of x1. Okay, and then this will surely be true with c equal to 1. Okay, and so the point is, if the weight b is a function of a single variable, then we have an additional considered quantity. And this might seem a special situation, but this exactly holds for axisymmetric order without swirl. So the weight is a function of, in fact, is the r coordinate. So for b of r and z equal to r, we have d dt of the integral of r squared omega of r z dr dz is 0. Okay, and so everything I've said until now applies to this so-called Lake equation in total generality. The first particular property we've seen for axisymmetric equations without swirl is they have one additional conserved quantity. That there may be some other special situations where you can find something like this, but in general, it's not going to happen. Okay, and so the only other special property of Euler equations in this situation of axisymmetry without swirl is that, well, that's what I've written here, is that though there's not exactly a good Biot-Savart law, but a Biot-Savart law. We can write down quite explicitly a formula for the inverse of the curl. So here's the, okay. So again, the Biot-Savart law, well, actually let me, let's, oops, sorry. So I want to, okay, so the basic properties are of Euler are, as far as I'm concerned, in 2D setting. Another basic property I should have mentioned is that there's a good well-posedness theory for this axisymmetric, in fact, for the Lake equations in general, and for axisymmetrical equations without swirl, because it's sufficiently like the 2D Euler equations that the same arguments developed there and still work. And so there's some analog of the Yurovich theory. The equations are well posed for initial vorticity in L infinity. And maybe on all of our, on an unbounded domain, you would need L infinity and L1. Okay, so then, right. So what about the Biot-Savart? In other words, I want to recover the velocity from the vorticity. And so remember, the way we do this is, well, in this setting, we want to solve the curl or grad perp dot u is omega, and the okay, and so this is what I would call the Biot-Savart law, and so our general procedure is, well, we look for a potential for u, and so earlier we wanted u to be curl free, and so we said, well, if it's a gradient, it'll be curl free. Sorry, we wanted u to be divergence free, which if it's a curl, it'll be divergence free. Here we want not u to be, we want b times u to be divergence free. And so let's say, so then the natural thing is we choose b times u to be a, we choose b times u to be, oh, geez, I'm totally. B times u to be Okay. So if we take b times u to be the orthogonal gradient of a scalar function psi, then it'll be divergence free in the sense. And for my sign convention is I always like to have minus Laplacian when I write the Laplace operator, and so I'll put a minus sign there to achieve that. And then in order for the boundary condition to be satisfied, we saw this before. We need psi. Well, sorry, we should ask. So we need. Then we need. So grad perp u, we need. And okay, and so then if I have these, if I define u in this fashion and I impose these conditions, then this here will correspond to the relation between velocity and vorticity, and this will enforce the boundary conditions as we saw before. And I can see I've just rotated both these operators grad perp by 90 degrees, and so I can get rid of the rotations if I would like to make it look better. That hasn't changed anything. Okay, and so so remember the way we found the Biot-Savart law earlier was we said, well, if there's no B, then this is just a question of inverting the Laplacian, and we have explicit formulas for that from PD classes. And in general, that's we can't for general domain D we can't do much more. Although actually there are good approximations for the so if I wanted to derive a Biot-Savart kernel for the Lake equation, I would I can't write down this formula in general, but one might be able to find a good approximation for the kernel for this psi, and indeed that's been done by in a recent paper of De Keyser and Van Schaftken. So so one can proceed by sort of approximations and analytic arguments, estimates. But in the case of axis symmetry without swirl, we can really write down an explicit operator if we choose, and that's the content of the next lemma. And so what I want is I'd like to okay. So here's the problem of reconstructing the velocity from the vorticity given omega, find a u with these properties and now h is the half space, and the weight is the one arising in this axisymmetric setting. And here's the problem that determines the potential psi. And okay, and so so here's the lemma, which and so the point is, well, they're formulas, and so and they're a little bit ugly, but well, they're not terrible. Unfortunately, we'll spend a little bit of time looking at them to see what they mean, because so the whole plan is to, as much as possible, redo our arguments that we used in studying the Euler equations in 2 dimensions, but for this in this sort of different setting. So we're seeing what changes. What changes is that the flow is no longer divergence free, or I mean the velocity field is no longer divergence free. It has this weight, and this means that the flow is not exactly Lebesgue measure preserving, but it preserves the Lebesgue measure with a weight. And the Biot-Savart kernel, well, it looks different. And this will change things when we try to repeat earlier arguments. But and so we need to understand how we will need to understand how different is the this kernel G, the axisymmetric kernel. And so you should think of G as being the analog of a log in 2 dimensions. For Euler in 2D, if you want to reconstruct velocity from vorticity, you convolve with a log. Here we have this axisymmetrized thing. So here I'm thinking of I'm writing things in polar coordinates. Well, yeah, this is this is r and z is above and happening. Okay, and then we also have a formula for the velocity. And so this is really the Biot-Savart law, so to speak. And so I've written it this way. So I'm writing u as a, so here's the r component, and here's the z component. And so if I look at this expression, the r component is here. I'll do this and erase it. Right, it's the coefficient of e sub r. That would be the r component of the velocity, and the z component is the coefficient of e sub z, similarly. So it's just a condensed way of writing that allows it to fit on a single line. And then we have an expression for the kinetic energy in terms of this axis symmetrized. So G is again, is the Green's function. This is like a log, if you like, and in this case, like the Biot-Savart kernel, like 1 over distance rotated. Okay, let's see if we can see where this comes from. And so let's just get the proof. And so we just have to remember where this problem comes from. We're considering a problem in a half space, but in fact, it's the 3D order, it's 3D elliptic equations in disguise. And so we'll define, so what I'm given an omega and I want to find a u and a psi. I'll define omega in R3 to be omega of R and Z times the unit vector in the theta direction in R3. And so again, you know, R is the distance from the z-axis, and so on and so on. And then let me see. So it's clear that this is 0. It's easy to check, but we know what the divergence means. We know this is purely rotational flow, and so its divergence got to be 0. Okay, and so we can find formulas for the associated velocity field, and say psi, the potential. Okay, we know what those are, and then we check that. That psi will have the form of some function psi of. Hold on. I wanted to write. I wanted to write it in this way. So I want I have to check my notes, excuse me. Right, psi of R, Z. I'll write it like this, times E sub theta. So I have some freedom in how to identify the vector field in R3 and the function R2. This turns out to be a smart way to do it. And U has the form. Okay, and so then we just define, and the point is that the known relations between the vector quantities imply the same the relations that we want between the quantities on the half plane. For example, U is the curl of psi, then is the same as saying that u on the half plane is the orthogonal gradient of psi over r, and maybe I want a minus sign someplace. Or omega is the curl of u. We'll say that on the half plane, omega is minus grad perp dot u, which I can express in terms of the stream function of psi if I wish. And similarly, the divergence of u is 0 will tell us that the divergence of RU is 0. Okay, so the point is we just lift it to this setting where we know everything about those formulas, write down the formulas, and then we can find from those the little u. We can find these quantities. So here's u is this thing, and psi is that thing. Okay, and so we'll go back here. What I'll do next time is I'll go through this quickly. I'll just sort of flash the formulas at you, because there's no point in writing that slowly. I'll flash the formulas at you, and we'll see where they come from. But so what happens is we write down formulas in R3, and then we just integrate out over the theta variable. And this is almost, but not quite, it's almost trivial. There's one little observation you have to make. And so, for example, the denominators we see in these expressions here and here, this is the distance between 2 points R prime and Z prime when the angle between them in the tangential space is alpha. And then so RZ and R prime Z prime, we integrate with respect to the angle, and we get these expressions, and then a cosine appears in the numerator for regions that will become obvious. Okay, so and so once we understand how this kernel works, we can begin proving theorems that tell us some meaningful information about solutions of the order equations in this setting of axis symmetry without swirl. And we can start doing that, I hope, well, depending on how quickly I flash the formulas in front of you, we can start doing this on Wednesday, I think, almost certainly. Okay, are there any questions about anything? Let me remind you again, let me recommend you the Fields Model Symposium. The funnest event today will be the opening thing, whatever it was, the public opening at 12:30 today. That'll be fun. And the other stuff will be of interest, if you're interested. It'll be good and interesting math talks. So, okay, I'll stick around for questions for a little while. And otherwise, I'll see you on Wednesday. Okay, let's Okay, let me see. I guess I'm going to close this, and I'll see you guys later.